Friday, hopefully you guys had a chance to either join or to watch the video that I did over power rule, which we'll review some more probably tomorrow or Wednesday. But today I want to talk about trapezoid. So using trapezoids to approximate an area of a region. We talked about multiple ways that we can use rectangles, but trapezoids is also another geometric shape that we need to be able to use to approximate a region. And then we'll talk about integral rules involving trig. And these, we should feel pretty familiar with these just because I asked you to memorize derivative rules from first semester for trig. And this semester, if you have those rules memorized, you're just working backwards from those rules. You're really just working backwards. So we're just undoing our derivative rules for trig. And we're going to talk a little bit, if we have time, we'll talk a little bit about how we can make our way up the chain. If we're at the second derivative level, we can take the antiderivative twice to move up to f prime and move up to f of x. So first semester, we're able to move our way down to the second derivative. And this semester, we can move our way back up that chain. Okay. So the pages in the packets are is not as well organized as I should have it. So we're jumping around the pages. So we'll start with page 10, and then we'll look at page 35, and then we'll look back on page 31. So we're jumping between those pages today. Okay, so here's page 10. So trapezoids are just naturally going to be better approximations of the curved region than either left-handed, right-handed, midpoint, inscribed, circumscribed rectangles. And if you look at the curve that we're going to approximate from example 1, those are variations of trapezoids there. And if you look at those trapezoids being drawn, there's already, even though we're using 6 regions here, you can already tell that trapezoids is going to have very minimal differences with the curve, right? I mean, it's obviously not exact, but it's a lot better than rectangles, right? Rectangles, you see all these corners either sticking out above or below, and trapezoids are just shaped better in terms of approximating a region. So sometimes on the AP exam, they will ask, oh, which of these approximations is the best for a curved region? And it's always going to be trapezoids being the best approximation, followed by midpoint. And then after that, the left and right, or inscribed, circumscribed are your next options. So here's the formula for trapezoid. This is maybe the orientation we're more used to, having 2 horizontal bases that are parallel to each other. And then the formula is 1/2 height, base 1 plus base 2, right? 2 horizontal bases. But the orientation that we're going to be using more often is, imagine taking this shape and flipping it on its side. So it'll look more like this. So instead of 2 horizontal bases, it'll be more like 2 vertical heights. So typically, there's different variations of it, but typically we're going to write it as 1/2 width, height 1 plus height 2. So okay, so this is the formula that we want to be able to use and to be able to memorize. Okay. And every trapezoid, there's only 2 heights associated with it. Okay, so we are going to, I will remind us of that over the course of our review. So I do see that sometimes students have trouble memorizing this area formula. So I want to see if I can connect it with something that we do know, and then hopefully that will having an anchor to compare with or to start with, I think maybe it's a little bit easier to memorize. So I want to start off with this shape here, right? Let's say we have a triangle, and let's say the triangle I'm going to call one side width and the other side height. What's the area of a triangle? Anybody remember? Width times height or base times height? Just base times height? Okay, because base times height is a rectangle, right? If you cut a rectangle in half, you're going to get a triangle. So, all right, so we're good with this, right? There's you guys all know this formula, right? So we're going to base off of this. A trapezoid is kind of like a triangle. It kind of looks like a well, at least the orientation that we're going to use. It kind of looks like a triangle sitting on top of a rectangle, right? So we know there's still a width involved, but there's kind of two heights going on, right? There's height 1 and height 2. So imagine you're building out your area of a triangle. Okay, so area is still 1/2 width, but then there's two heights involved. So instead of times height, it's going to be times height 1 plus height 2. So I'm hoping that helps in terms of allowing you to memorize this a little bit easier. If you know the area of a triangle, and if you can draw out a trapezoid, you can tell that, okay, it's really two vertical heights. So I'm just going to adapt my area of a triangle. Instead of one height, I'm going to add the sum of two heights. Right, but we do need to memorize this formula. It's going to show up on the AP exam, and we're going to be tested on this on the quiz as well as the test for this unit. So example 1 says, estimate the area bounded by the function f of x equals 6x minus x squared and the x-axis using 6 trapezoids. Now, if you look, this looks like two triangles and multiple trapezoids. So if I have triangle, I can still use a trapezoid because one of the heights will just end up being 0, and it'll turn itself into a triangle formula. So we don't have to worry about, oh, we got to build out a different formula for trapezoids, for triangles. It'll just turn itself into a triangle if it needs to. So the x-intercepts ends up being 0 and 6. So we have an area of, the width formula for our interval is going to be b minus a over n. So 6 is my right endpoint, 0 is my left endpoint. So 6 minus 0 over 6, which is 1. So this is nice. Every increment is by 1. So 1, 2, 3, 4, 5, and 6. So we're just going to make every one of these go through an area formula for trapezoid. So the area is approximated by, now there's a lot of these here, so it's going to feel like now we're doing a lot of calculations here. But the first trapezoid or triangle is 1/2 times the width. My width is 1. And then height 1 plus height 2. And to find the heights, I'm going to take the 0 and 1 and plug it into the function. So I'm going to leave it in function notation here. So f of 0 plus f of 1. Okay, second trapezoid. I'm going to shade in the second trapezoid here. So same process, right? The width is the same, still that 1/2, and then f of 1 plus f of 2. And then we're just doing this 6 times. And define f of 0, f of 1, f of 1, f of 2. We just plug into the function here. And that's just a lot of tedious calculations, but it ends up giving us 35. And that's really it for trapezoids. Instead of width times height, it's width times height 1 plus height 2. There's always going to be 2 heights associated with every trapezoid area that we find. Okay. I want to show you a lot of what the AP exam is going to look like in terms of Riemann sums in terms of using rectangles to approximate a region. Typically, the AP exam is going to show you a table and then ask you to pull the values from that table. So page 35, we can get a chance to look at what Riemann sums will be presented like on the AP exam. So this isn't hard, but once you get it, you're going to get it. It's going to feel easy, hopefully, and then but I do want to make sure that we are setting things up correctly, because I see some students, didn't quite learn it correctly the first time, and they just end up struggling. And it should be easy. They're just pulling the information not quite the correct way. So I want to show you how we can use left rectangles, middle rectangles, right rectangles, and trapezoids, or pull those approximations from the table of values. All right, so we have selected values of function are given in the table. So we have a bunch of order pairs. We don't know what the graph looks like. We just know that the graph is going to hit these points. Okay. So we don't have to worry about how well our approximation is. I think that the main picture is that, okay, we know trapezoid will be the best approximation. Middle is the next best, and then left and right. But you're not going to have to be able to tell, how accurate this approximation is. We just have to be able to find these approximations. So it says give the middle approximation with 3 subintervals on the interval from 0 to 20. We're not going to use the b minus a over n because every interval may have a different width. Okay. Now, middle is in quotes. Okay. Middle approximation, we're not going to quite do midpoint. I see some students trying to force a midpoint. They try to find, what's the exact middle? Middle is relative in relation to these order pairs. So we want 3 subintervals from 0 to 20. So that means every subinterval is going to see the same number of order pairs. Okay. So you're going to basically count, right? You have 1, 2, 3, 4, 5, 6, 7. There's 7 order pairs, and every order pair, every interval is going to see the same number of order pairs. So what if we did this? What if the first interval is from 0 to 8, and then the second interval is from 8 to 12, and then the third interval is from 12 to 20. Now, when you draw your intervals, you're always going to start at the middle of your order pair and end at the middle of your last order pair. And then your second interval is going to pick up where you left off. You're always going to have a shared order pair to move on to the next one. Right? We don't want to do 1, 2, 3, and then the next one starts with the fourth one. You're always going to have a shared overlapping endpoint from one interval to the next. Okay. So it's three subintervals in the sense that it's three subintervals based off of the order pairs given to us. So every order pair spans, every interval spans across, in this case, three sets of order pairs, right? But the width may not be the same, but the interval is, we're using the intervals defined by the table. Now, when we want to, we're talking about middle rectangles here. This is middle Riemann sums. So rectangle is width times height. So to find the width, you're going to be subtracting the distance between your first and your last endpoint. In this case, the 5, the 9, and 18 is not going to play a role for us. So 8 minus 0 is going to be the width of my first rectangle. So 8 minus 0 equals what? 8. So that's the width of my first rectangle. Okay. What's 12 minus 8? 4. That's the width of my second rectangle. What's 20 minus 12? 8. That's the width of my third rectangle. So that's how I pull the width information for each of my rectangles from subtracting the terms from the first row. Now, to find the heights, it's going to come from your second row. So middle, it's going to come from this 5 here. I know 5 is not quite the midpoint from 0 to 8, but we don't have to worry. As long as we're just going to use whatever is in between. It could be 7, it could be 1, it could be 2, but we want to pull the y value that is quote unquote in the middle. Middle just means it's between my left and right endpoint. Right. So my first rectangle will have a width of 8 and a height of 2. My second rectangle will have a width of 4 and a height of 7. And my third rectangle will have a width of 8 and a height of 6. Okay, so we're just going to add those together. Check my notations here. I see some students trying to find the average of two numbers, and they'll say, oh, midpoint. So they find the average between 0 and 8, and then divide it by 2. So we don't want to do that. Right? Middle just means whatever is in between. So, all right, part B, use right-handed rectangles to approximate the area with 3 subintervals from 0 to 20. So sometimes, just be careful. Sometimes the interval may not span the entire table. And then sometimes the region is not always 3 subintervals. So pay attention to your interval, pay attention to your endpoints. Okay, but in this case, we can use the same intervals, right? So 0 to 8, 8 to 12, and 12 to 20. Make sure that you're subtracting the endpoints. I see some students adding the 2 endpoints. So you want to find the distance between the 2. That's your width. And then 12 minus 8 is 4. 12 subtracted from 20 is 8. But we want right-handed rectangles. So for the first interval, what do you think we're going to choose? The 4, the 2, or the 3 as the height? 3. Yeah. So we're going to choose the corner that is at the right of each subinterval. So my first rectangle will be width times height, 8 times 3. Second rectangle will be 4 times 3. Third rectangle will be 8 times 10. Part C, use left-handed rectangles to approximate area with 3 subintervals on the interval from 0 to 9. Okay, what's different about part C? Like, we still have 3 subintervals, still the same table, but what's different? 0 to 9. So now every subinterval may not see as many ordered pairs. So from 0 to 9, I'll go from 0 to 5, 5 to 8, and 8 to 9. So these are my subintervals now. 0 to 5, 5 to 8, 8 to 9. I'm still going to subtract the width, the x values to get the width. It's a left-handed rectangle, so which height do I want to choose for my first subinterval? 4. Now, second subinterval will be 3 times 2. Last subinterval will be 1 times 3. And I'm using the squiggly line to indicate this is just an approximation. We don't know the exact area. We're just using limited information we have. Any questions so far? Some students have asked, wait, so this is, we can do left-handed rectangle, we can do right-handed rectangle, but what do we do if this was being asked how to find the midpoint rectangles? And the answer to that question is you're not going to be asked to do a midpoint rectangle if there's not a middle point to choose from. Okay, so if it's going to be a middle rectangle, I've got to give you an odd number of ordered pairs so you can actually pick out a middle one to pick from. You're not going to have to do additional calculation to find the middle. On the AP exam as well, if they're asking you for a middle rectangle, they have to give you some order pair to pick from that sits in between. So if there's only 2 endpoints of your within your subinterval, you're only going to be asked left and right. You won't be asked the middle. Okay, part D, trapezoids. We're doing 2 trapezoids spanning from 0 to 20. Okay, so how can we split this up so that each subinterval can see the same number of order pairs? First subinterval is from 0 to what? 9, okay. And then the next one will be from 9 to 20. Let's double check. 0 to 9, that spans across 4 order pairs. And then second subinterval spans across 4 order pairs as well. Okay. All right, 9 minus 0 is 9. 20 minus 9 is 11. Now, area of a trapezoid is 1/2 width, height 1 plus height 2. Again, it kind of resembles triangle formula, right? But we're only going to pick out 2 heights for every trapezoid. So guess which 2 heights we're going to choose for the first subinterval? For the first trapezoid, sorry. Good. Just the ones where your vertical lines are coming down. So 1/2 times 9, 4 plus 7, and then 1/2 times 11. And what do we choose for the second subinterval? Second trapezoid, 7 and 10. I do want to point out a common mistake that students make, and I want to show this to you in the hopes that you will avoid it. Some students, they feel like, oh, like they're missing out on these numbers. And they have to include those numbers somehow. So they start doing this, 1/2 times 9, and then they want to add up all these numbers together. So they do 4 plus 2 plus 3 plus 7. And then for the second trapezoid, they'll do 1/2 times 11, and then they'll do 7 plus 3 plus 6 plus 10. Okay. We don't want to do that. Okay. Then we're creating something else. This is not the area formula of a trapezoid. So make sure that for every trapezoid that you're building, you're only picking out 2 heights. Whether there's any ones that are in between, you're going to have to learn to ignore it if you see those ones that span across multiple order pairs. Hopefully you guys find this easy. I try to point out as many of the common mistakes that students make in terms of sometimes they would get the 2 mixed up between the height and the width. They would either add or subtract incorrectly, or they would pick out everything from the first row and not even look at the second row. So, but just know that your width comes from information from the first row, and then your height comes from information from the second row. Okay. Let's go back to page 31. This is the last section of our quiz topics. Okay, let's think back on first semester here. Let's review our trig derivative rules, right? I had them all. We have them all memorized in terms of organizing them from 2 corners here, 2 columns here. So what's the derivative sign of u? Yeah, cosine of u times u prime. Okay. What's the derivative of cosine of u? Negative sine of u times u prime. Yep. We know that tangent and secant derivatives just involve each other. So we remember what's tangent's derivative? Secant squared. Sorry for all these stray marks here. And then we know cotangents also involves itself or cosecant. So what's cotangent's derivative? Negative cosecant squared. All right, what's secant's derivative? Secant u, tangent u. And then cosecant, negative, yeah. So my suggestion is that don't feel like you have to memorize a new set of integral trig rules. My suggestion is you just memorize the 6 derivative rules and just know that your antiderivative is just working backwards from your derivative rule to your original function rule. So let me ask you this. If the derivative of sine is cosine, what's the antiderivative of cosine? Sine, right? So the antiderivative of cosine is equal to sine. And so that's the notation that we're going to see here. The antiderivative of cosine is simply equal to sine of u plus c. And if you're thinking, wait, what happens to that u prime? That u prime is basically taking that role of that du there. So don't have to worry about that u prime. Antiderivative of cosine is equal to sine. So it really is as easy as just reading backwards. Okay, whatever you see on the right side, you're just working from the right of your formula to your left. What's the antiderivative of secant squared? Guess what? Right? If tangent's derivative is secant squared, then the antiderivative of secant squared must take us back up to what? You see it? Back up to tangent, right? Okay, so we find that rule here. Sorry, I didn't mean for it to look like all these negative signs here. These are all kind of stray marks here. So the antiderivative of secant squared is just tangent of u plus c. All right, what's the antiderivative of secant u tangent u? Just secant, yeah. What's the antiderivative of negative sine of u? Cosine. But then what if I were to make it the antiderivative of a positive sign? Negative cosine. So this is where the tricky, I think some students have trouble with this, is that sine turns into a negative cosine of u plus c because we're going backwards, okay? Because we're asking for the antiderivative of a positive sign, the negative has to go somewhere, so the negative has to transfer over on the right side. You know, even though we're just working backwards from these rules, these are the ones that give students the most trouble. The antiderivative of sine is negative cosine, and the antiderivative of cosine is a positive sign. Why do you think these give students trouble? Right, it's opposite of what we expect, right? Because from a derivative standpoint, we're so used to sine being cosine and cosine being negative sine that when things are backwards, it's easy to feel like for students to say, oh, cosine, oh, that's a c, so I'm going to put a negative, and the sine is a positive cosine. But you're working backwards here. And again, there's no need to memorize these rules. If you just look at the rule on the right side and work backwards to the left, you should be able to convince yourself, okay, if there's that negative there, it has to go somewhere. It's going to go with the sign. So just be careful with these two. These tend to give students the most trouble. Cosecant squared. Cosecant squared will produce a negative cotangent. That negative has to go somewhere. And then cosecant of u, cotangent u, the negative has to go somewhere. So negative cosecant of u plus c. So again, on the quiz, I expect you to, my suggestion is just review your derivative rules, write your derivative rules down at the top of your page, and then just refer to it in terms of reading backwards, and that's your antiderivative rule. Okay, on the quiz, it really is just going to be, okay, let me give you an example of a quiz question here. where it won't look like these classical problems that I gave you. It'll be more like this. I say I asked you for the integral of cosine of x plus sine of x minus cosecant squared of x dx. Every term has its own antiderivative rule, and we just find those rules. So cosine's antiderivative is sine. Sine's antiderivative is negative cosine. Cosecant squared turns into So cosecant squared will produce its own negative cotangent, and the two negatives will cancel out. So plus cotangent of x. And then you got to include a plus c because we have a family of functions that all share the same derivative as this. So on the quiz, you're just really have to know how to work the integral rules from the derivative rules that you learned from first semester. Okay, next page. Okay, so first semester, we learned all about how being able to find the derivative. So this semester is about working backwards. Can we get from the derivative level back up to the function level? So let me skip 3 and 4. I just want to talk about the process that we already know how to do. So let's say we're starting with y prime. So y prime is kind of like your f prime. Your f prime is 3x minus 4. So if I want to find my f of x from my y function from my f prime, I got to take the antiderivative. So I know that y, which is equal to f of x, must be found by taking the antiderivative of my derivative function. So we're undoing the derivative process by taking the antiderivative. Okay, so I went over this in our notes from Friday that when we take the antiderivative, we're adding 1 to the exponent and divide it by that new exponent. So 3x becomes what? 3x squared, good, over 2, right? And then 4, what does minus 4 turn into? Good, minus 4x, right? Every degree is going to rise by 1. But each time we take the full antiderivative, we also need to include a plus what? Plus c. Okay. So this tells us that there is an infinite family of functions that all share the same derivative, but we now have an order pair that's going to help lock down a specific location or specific solution. So we're going to use the order pair here to help us solve for c. So the 4 is going to plug in for x. The 10 will plug in for y. And that will help us pinpoint the specific solution for this antiderivative. It has to fulfill this order pair. So 10 will go in for y, and 4 will go in for x. Okay. And then we're just solving for c here. So I have 16 over 2 is 8. 8 times 3 is 24. And I get c is equal to 2. Once I get my C value, I'm just going to take that C value and update my general equation. We call this a general solution whenever there's a C involved, but a specific solution is when that C gets replaced with a number. Yes. Oh, right here. I just pulled the 3/2 out in front and I made it 3/2 x squared. Because 3x squared over 2 is same thing as 3 over 2 times x squared. But you know, if you wanted to, you could put the 2 underneath here and I'll be fine. You'll still get the same answer. 3 times 16 is 48. 48 divided by 2 is still 24. Is that what you're asking about? Okay. Oh, you're asking how does this 2 get here from the antiderivative from the integral rule? Or okay, right. So the rule is u to the n plus 1 over n plus 1. So with derivatives, we subtracted 1 and we subtracted and we multiplied, right? So the antiderivative process is undoing that process. We're going to be adding and dividing. So for instance, if I were to find the derivative of 3/2 x squared, this will bring me back to 3x. Yeah. Right, so power rule for antiderivatives, we're going to be adding 1 to the exponent and divided by that new exponent. Okay. Page 33. Okay, so now let's say we're starting with f double prime and we're trying to find f of x. Okay, so we're going to take the antiderivative twice from f double prime to f prime, and then we can update our c value, and then from f prime to f of x, update that c value as well. So if I want to find f prime, I'm going to take the antiderivative of 6x plus 4. So just like first semester, we're able to make our way down to the second derivative by taking the derivative twice. So now we're trying to take that second derivative and kind of make our way back up that chain to the original function. Okay, so let's take the antiderivative to get up to the f prime levels. We're starting at the f double prime, trying to make our way up to the f prime level. So 6x becomes what? Yeah, 6x squared over 2, right? 4 becomes 4x, and then plus c. Yeah, so we have f prime, the general solution for f prime. We have an ordered pair at the f prime level. So we can plug 0 in for x and 3 in for the f prime. And then we can solve for c. So when I solve for c, I got c equals 3. So I'm going to take my c equals 3. I'm going to update my f prime. And then I can take the step up to f of x. Right, so we're officially halfway there. We'll take the antiderivative again to make our way from f prime to f of x. So we know f of x can be found by making that f prime go through another antiderivative process. So we go through power rule again. 3x squared becomes What happens to that 2? Yeah, 3. And then divide by what? 3, yeah. 4x becomes 4x squared over 2. 3 becomes 3x, and then plus its own c. I'm going to call it c sub 2 just because I don't want to. I want to make sure this c is different from this c, so I'm just going to just give myself a slightly different name. But we have a order pair at the function level that we can plug in to help us solve for this c value. Right? So 1 can plug in for x, 5 can plug in for the y. So I have my other c value being -1. So now I can update my function f of x with a specific solution. Okay. Now think back on first semester here. We should be able to, first semester, we're able to take our f of x and make our way down to f prime, right? So f of x becomes, or f prime will be 3x squared plus 4x plus 3. 3x squared plus 4x plus 3. That's what we have, right? And then from f prime, we're able to find f double prime, 6x plus 4, 6x plus 4. Right? So first semester, the easier process was finding the derivative, and this semester, a bit more challenging is taking the antiderivative because we have to take the additional step of solving for those constants as we move up that chain. All right, just one more thing here. So if you can turn to page 34. So page 34, this is the formula sheet that I will provide for you on the quiz, except for trapezoid. Okay, so this I do need you to memorize. Okay? But everything associated with the area definition of a limit, the width, the summation, I will give those to you. Now, tonight's homework, you guys are going to do the homework that was assigned for Friday, which is 4.1a power rule integrals. So page 251 to 252, number 7 to 23 odds. Right. So we're just staggering each of our homework from last week. And this is what we're going to do tomorrow. If you can turn to page 37 real quick. So tomorrow we'll work on our quiz review, which is page 37 to page 38. Now tomorrow I may or may not be here. So that's why I wanted to do this for tomorrow. So if I'm not here, you guys will just do this page 37 and 38 as your classwork. And then I will have the key. When you come in, you'll have the key to pick up to kind of check your work. And then I will update you on what the homework is for Tuesday, which is to okay, I can make your phones. Okay, sure.
And I'll hold it. So I don't think so. Thank you.
Thank you.
I also. Oh, yeah. Sorry. Pictures open when I was still.